Hello everyone, my name is Priya. I am from BSc Chemistry Honors सेकेंड ईयर। आज हम करने वाले हैं हमारा फिजिकल केमिस्ट्री का चैप्टर डिस्ट्रीब्यूशन लॉ। इसके लिए हमने मॉडर्न अप्रोच की किरण की हमारी फिजिकल केमिस्ट्री की बुक ली है। हम इंट्रोडक्शन से स्टार्ट करते हैं। डिस्ट्रीब्यूशन लॉ। Nernst distribution law studies the distribution of a solute between two immiscible solvents in contact with each other. When a solute soluble in two immiscible solvents is added to a mixture of these solvents, the concentration of solute in both the solvents layers is different. In other words, the solute distributes itself in both the solvents. For example, when a dilute solution of iodine in water shaken with carbon tetrachloride, the iodine distributes between two immiscible solvents. Iodine is about 86 times more soluble in carbon tetrachloride than in water. Due to higher solubility, most of the iodine passes into CCl4 layer. In simple words, iodine is distributed between two immiscible solvents, water and carbon tetrachloride. Nernst in 1891 showed that when a solute is added to a mixture of two immiscible liquids, in both of which it dissolves, then it distributes itself between both the liquids in such a way that the ratio of concentrations of the solute in both the liquids remains constant at constant temperature. However, this ratio is constant only when the solute has same molecular state in both the solvents. The solute neither undergoes association nor dissociation in both these solvents. The generalization put forward by Nernst is called Nernst distribution law and is stated as a solute distributes itself between two non-miscible solvents in contact with each other in such a way that at equilibrium the ratio of the concentration of the solute in the two layers is constant at a given temperature, provided the molecular state of solute is same in both the solvents. If a solute X distributes itself between solvents A and B as figure 1, the distribution law is written as concentration of X in solvent A upon concentration of X in solvent B is equal to C1 upon C2 is equals to K. The constant K is termed as the partition coefficient or distribution coefficient. Factors affecting partition coefficient. Nature of solute, nature of liquid pair, temperature. Nature of solute. For a particular liquid pair, different solutes have different solubility. Hence, the value of partition coefficient will be different for different solutes at a given temperature. It is clearly seen from the data in the table given below. There are examples of solute benzoic acid and succinic acids. Nature of the liquid pair. A given solute has different partition coefficient in different liquid pairs as shown in the table below. Solute is succinic acids same. Their partition coefficients value is different. Temperature. The solubility of a solute in a particular solvent changes with temperature. As the temperature is changed, the solubility of a solute in a given liquid pair also changes. Therefore, temperature is called the solubility of a solute in a given liquid pair also changes. Therefore, the partition coefficient also changes with temperature. The change in value of partition coefficient for 1 degree rise in temperature is shown as temperature coefficient. However, the value of temperature coefficient is generally small. Table below shows value temperature coefficients for some systems. Experimental verification of distribution law. Solutions of iodine in carbon tetrachloride of different concentrations are shaken with water taken in different bottles. These are allowed to stand undistributed till the two layers separate out. A known volume of CCl4 layer and aqueous layer is pipetted out and titrated against standard sodium thiosulfate solution and the concentration of iodine is determined. The following results from the distribution of I2 between CCl4 and water show the constancy of ratio of concentration in each layer. Hence prove the validity of distribution law. These results show that the ratio C1 upon C2 is almost constant. Hence the distribution law is valid in this case. Conditions for validity of distribution law. Limitations of Nernst distribution law. The distribution law in its simple form K is equals to C1 upon C2 does not hold under all conditions. Some limitations and the conditions under which the law is applicable are as follows. Temperature should be kept constant. The solubility of a solute in both the liquid changes with change in temperature. This may result in change in concentration in both the solvents. Moreover, change in temperature may affect the mutual solubility of the two solvents. Therefore, with change in temperature, a different value of partition coefficient is obtained at every temperature. Hence, the temperature should be kept constant throughout the determination of partition coefficient. The two solvents should be immiscible or sparingly soluble. The mutual solubility of the two solvents should not be affected by addition of solute. The solutions should be dilute. Distribution law holds good for dilute solutions. As the concentration of solute increases, the derivations from distribution law becomes more and more pronounced. The molecular state of solute should be same in both the solvents. This law is not valid under following two conditions. When the solute undergoes association, the law in simple form is not applicable when the solute undergoes association in any of the solvents. For example, distribution law does not hold for phenol distributed between benzene and water because phenol undergoes association in benzene to form dimers. When the solute undergoes dissociation, the distribution law is also not valid for solutes which undergo dissociation in any of the solvents. For example, electrolytes like HCl undergoes dissociation in water and hence its solution in a mixture of water and an organic solvent does not obey distribution law in its simple form. Modification of distribution law with change in molecular state of solute. Nernst showed that the ratio C1 upon C2 is constant is applicable only when the solute has the same molecular conditions in both the liquids. That means the solute does not undergo association or dissociation in any of the liquids. However, if any of such changes takes place in one or both the liquids, then the distribution law gets modified. Let us consider cases in which a solute may associate or dissociate or enter into chemical combination with one of the solvent. When the solute undergoes association in one of the solvents, suppose a solute X remains in the normal molecular state in phase 1 whereas in phase 2 n molecules of X undergo association to form complete molecules Xn. Solute X undergo association in solvent 2, here two equilibria exist simultaneously. Suppose the total concentration of the solute X in phase 1 is C1, the total concentration of solute X in phase 2 is C2. If alpha is the degree of association of solute in phase 2, then the concentration of associated molecules in phase 2 is equal to 1 by NC2 alpha. The concentration of normal molecules in phase is equal to 1 minus alpha into C2. Applying distribution law to the distribution of X in the two solvents, we can write concentration of X in phase 1 upon concentration of normal molecules of X in phase 2 is equals to K. C1 upon 1 minus alpha into C2 is equals to K. Applying law of chemical equilibrium to the polymerization process, Nx is equal to X, and we can write the equilibrium constant K equilibrium as concentration of associated molecules in phase 1 upon concentration of normal molecules in phase 2 is equal to K of equilibrium. Taking nth root on both sides, n root of C2 alpha upon 1 minus alpha into C2 is equal to constant. By this equations we get C1 upon n root of C2 is equal to constant. This relation is used in determining the value of n, the extent of association of molecules. The values of C1 and C2 are determined experimentally and substituted in equation. Putting n is equals to 1, 2, 3 etc. The value for which a nearly constant value of K is obtained is equal to n. Equation 4 has been verified by studying the distribution of benzoic acid between water and benzene. Benzoic acid exists almost entirely as dimers in benzene but in normal state in water. This is the table between benzoic acid and water. Evidently the ratio C1 upon C2 is not constant, hence benzoic does not exist as single molecules in benzene. A fairly constant value of C upon root C2 shows that the benzoic acid exists as dimers in benzene. The methods to calculate N has been explained in section 8.0. When the solute undergoes dissociation in one of the solvents, let the solute X dissolve in phase 1 in its normal state and undergoes dissociation in solvent 2 as shown in figure 3. The two equilibria exist simultaneously are total concentration of X in phase 1 is equal to C1 Total concentration of X in phase 2 is equal to C2. The degree of association of solute in phase 2 is equal to alpha. The concentration of undissociated molecules in phase 2 is equal to 1 minus alpha into C2. Applying distribution law, the ratio of concentration of solute in equilibrium is given as this. On the other hand, when the solute is dissociated in phase 1 having degree of dissociation alpha and remains undissociated in phase 2, then the partition coefficient is given by C1 1 minus alpha upon C2 is equals to K. When the solute is dissociated in both the solvents, it is evident from the figure 4 that the concentration of the solute in layer first is C1 into 1 minus alpha and in layer 2 is C2 into 1 minus alpha. Where alpha is the degree of dissociation of the solute, the partition coefficient is given by C2 upon C1 into 1 minus alpha is equal to K. Case 4. When the solute enters into chemical combination with one of the solvents, suppose the solute X remains in normal molecular state in solvent 1, but one molecule of X combines with n molecules of solvent in phase 2 to form X dot N dot S molecule. Following equilibria exist simultaneously. Let the concentration of solute X in normal state in phase 1 is equal to C1. The concentration of X in normal state in phase 2 is equal to C2. Concentration of solvent molecules in phase 2 is equal to Cs. Concentration of complex molecules in phase 2 is Cc. Applying distribution law to equilibrium first, we get C1 upon C2 is equal to K. Applying law of chemical equilibrium to equilibrium second, we get Cc upon C2 into Cs is equal to K1. In dilute solution, the concentration of solvent in phase 2 is in excess. Therefore, its concentration Cs remains particularly constant. Thus, equation 2 takes the form Cc upon C2 is equal to K1 into Cs dash is equal to K2. Adding 1 to both sides, we get this. Dividing equation 1 by equation 3, we get this. C2 plus Cc is equal to total concentration of normal molecules and solvated solute molecules in phase 2. Therefore, equation of 4 may be written as total concentration of solute X in phase 1 upon total concentration of solute X in phase 2 is equal to constant. It is evident that when the solute molecules enter into chemical combination with solvent molecules, the distribution law does not get modified. However, there is change in the numerical value of the constant. Thermodynamic derivation of the distribution law. The derivation of distribution law from thermodynamics is based on the condition that in a phase equilibrium between two immeasurable liquids containing the same solute dissolved in them, the chemical potential of the solute must be same in both the phases. Suppose a solute is present in two immeasurable solvents A and B in contact with each other. The chemical potential in solvent A is mu A and in solvent B is mu B. At equilibrium, the chemical potential of the solute in both the phases is equal. From thermodynamics, we know chemical potential of a substance is given as where mu naught is the standard chemical potential and A is the activity of the solute in solution. At constant temperature, the standard chemical potential mu naught A and mu naught B for a given solute in a particular solvent are constant. Since R is also constant, it follows from equation 5. Since the solutions are dilute, therefore the activities are equal to the concentration. So the equation 7 becomes Ca upon Cb is equal to constant is equal to K. This is the Nernst distribution law. It is applicable in this form when the solute is normally distributed in both the layers. However, it gets modified in the cases when the solute undergoes association, dissociation or enters into chemical combination with one of the solvents. Applications of distribution law. There are many applications of distribution law in laboratory and in industry. Some of these are briefly discussed here. In calculating solubility of a solute in a solvent, when a solute is shaken with two immiscible solvents in contact with each other, at equilibrium both the solvents are saturated with the solute. Therefore, the concentration at equilibrium are equal to the solubility of solute in both solvents. We can write the distribution law as C1 upon C2 is equals to S1 upon S2 is equals to K. C1 is equals to S1, the solubility of the solute in solvent 1. Concentration C2 is equals to CS2, the solubility of the solute in solvent 2. Hence, knowing the value of the distribution constant and solubility of the solute in one of the solvent, the solubility in other solvent can be calculated. Distribution indicators. Certain solvents are appreciably dissolved even the small amounts of solute present in some other solvents. When such a solvent is added to a dilute solution of solute in some other solvents, most of the solute gets distributed into this solvent. Hence, it acts as an indicator for the presence of even a small amount of the solute. For example, a dilute solution of iodine in water is almost colorless. Iodine is considerably soluble in CS2. Its distribution coefficient between CS2 and water is 400. Therefore, as extremely dilute solution of iodine can be estimated by adding a few drops of CS2 to its aqueous solution. A sufficient amount of iodine passes into CS2 layer and gives it a deep violet color. This solution may be titrated against hyposolution till the violet color in CS2 layer disappears. Hence, CS2 can serve as distribution indicator in iodomeric titrations in which iodine is produced during titration. In determining the extent of association or dissociation of a solute in a solvent, using distribution law, the molecular state of a solute in a solvent can be determined in the distribution experiment if the ratio of concentrations of solute in both the solvents C1 upon C2 is constant, then the solute behaves normally in both the solvents. When a solute X undergoes association in one of the solvents having concentration C2 in it, then the distribution law modifies as from the value of N, the molecular mass of the solute in this solvent can be calculated by multiplying the actual molecular mass by N. For example, benzoic acid in a mixture of water and benzene exists as dimer in benzene. Hence, the value of N is equals to 2. Therefore, the molecular mass of benzoic acid in benzene is 2 into 122 is equal to 244. The value of N in above expression can be calculated by one of the following methods. By hit and trial method, the values of C1 and C2 are obtained experimentally and C1 upon n root C2 is equal to K are put in the following equation. Then putting n is equals to 2, 3, 4, the corresponding values of K are calculated. The number which gives a constant values for K is the correct value of n. Logarithmic method. We have the equation C1 upon n root C2 is equal to K. C1 upon C1 by 2 n K. C1 is equals to C2 1 by n into K. Taking logs on both sides, we get log of C1 is equals to 1 by n log of C2 plus log of K. For two experimental values C1, C2 and C1 dash C2 dash, we can write log of C1 is equals to 1 by n log of C2 plus log of K, and log of C1 dash is equals to 1 by n log of C2 dash plus log of K. On subtracting equation 2 from equation 1, we get log of C1 minus log of C1 dash 1 by n log of C2 minus log of C2 dash. N is equals to log of C2 minus log of C2 dash and log of C1 minus log of C1 dash. Hence n can be calculated. Similarly, when a solute dissociates in one of the solvent in which its concentration is C2, but then the distribution law is applicable as C1 upon C2 into 1 minus alpha is equal to K. Thus, if the degree of dissociation of the solute is known at one concentration, the value of alpha at any other concentration can be obtained using above equation since K is constant. In the study of chemical equilibrium involving formation of complex ions, an important application of distribution law is to study the equilibria involving complex ions. Consider some reactions involving formation of complexes ions are Ki plus I2 is equals to Ki3, Kbr plus Br2, Kbr3 and etc. Using distribution law, the equilibrium constant of any of these reactions can be calculated on the basis of constancy in the values of equilibrium constant. The formula of the complex can be found out. The application of distribution law in determining the formula of complex ion I3 minus is described as below. A solution of iodine in CS2 is shaken with water to determine the distribution coefficient of iodine between CS2 and water. A solution of iodine in CS2 of known concentration, say a moles per liter, is shaken with an aqueous solution of Ki of known concentration. After the equilibrium is stabilized between two layers, the concentration of iodine left in CS2 layer is determined volumetrically by titrating it against standard hypo solution. The equilibrium constant is calculated as follows. Let the initial concentration of iodine in CS2 layer is equal to A moles per liter. The initial concentration of Ki solution is equal to B moles per liter. Distribution coefficient of I2 between CS2 and water is equal to K. Concentration of I2 left in CS2 layer is equal to C moles per liter. In aqueous layer, I2 reacts with Ki, therefore total concentration of iodine in aqueous layer will be much higher due to formation of soluble complex AI3. Total concentration of I2 free plus combined in aqueous layer. Initial concentration of I2 in CS2 minus concentration of I2 left free in CS2 layer is equal to A minus C moles per liter. Concentration of free I2 in aqueous layer can be calculated according to distribution law. Concentration of free I2 in aqueous layer upon concentration of I2 in CS2 layer is equal to K. But the concentration of I2 in CS2 layer is equals to C moles per liter. Concentration of free I2 in aqueous layer is equal to Kc moles per liter. The concentration of I2 that has combined with Ki is equal to A minus C minus Kc moles per liter is equals to D moles per liter. According to the reaction, Ki plus I2 is equal to Ki3. Number of moles of I2 combined is equal to number of moles of Ki3 combined is equal to number of moles of Ki3 formed. Concentration of Ki3 in aqueous layer is D moles per liter. Concentration of Ki in aqueous layer is B minus D moles per liter. Concentration of I2 in aqueous layer is Kc moles per liter. Applying law of chemical equilibrium, we can write K dash is equals to Ki3 upon Ki dot I2. Taking different initial concentrations of I2 and Ki solutions, the values of K dash is calculated for each set. The constancy of value of K dash shows the formula of complex is Ki3, for that of complex ion is I3 minus. In the process of extraction, another important application of the distribution law is in the process of extraction in laboratory as well as in industry. In laboratory, for instance, it is frequently used for the removal of a dissolved organic substance from aqueous solution with solvents such as benzene, ether, chloroform, carbon tetrachloride, etc. The advantages is taken of the fact that the partition coefficient of most of the organic compounds is largely in favor of organic solvents. In industry, the process of extraction is used to remove the impurities from the product. The aqueous solution of the substance to be extracted is shaken with an organic solvent in which it is highly soluble. After shaking vigorously, the mixture is allowed to stand for some time. The two layers are then separated using a separating funnel. The organic solvent is recurrent by distillation and used again. For the extraction process to be more efficient, following conditions should be fulfilled. The distribution coefficient of the substance between the extracting solvent and the solvent in which it is already dissolved should be very high in favor of extracting solvent. Sometimes the distribution coefficient in the extracting solvent is artificially increased by making the substance less soluble in the aqueous phase. This can be done by adding some substance which decreases the degree of dissociation of the compound in aqueous phase. For example, acetic acid, which weakly ionizes in aqueous solution, is to be extracted with ether. A strong acid, say HCl, is added to the solution. Due to the ionization of HCl, the H plus ions concentration increases, and due to the common ion effect of ionization of acetic acid is suppressed. As a result, there is greater concentration of unionized acetic acid, hence greater amount of acid will be extracted in ether layer. Similarly, the extraction of organic base from its aqueous solution into organic solvent can be increased by adding strong inorganic base. In general, the solubility of an organic compound in water can be decreased by adding salts, hence its distribution coefficient increases in favor of extracting solvent. This is termed as salting out effect. Thus, we conclude that greater the distribution coefficient in the favor of organic solvent, greater will be the amount extracted. To recover the maximum amount of substance, the extracting solvent should not be used in one lot. Rather, it should be used in maximum number of installments. This is called multiple extraction or multi-step extraction. The fact that it is more efficient to use extracting solvent in small portion rather than in one lot is illustrated as follows. Suppose Ag of the substance is present in 1 liter of aqueous solution. We can extract the substance with ether as the distribution coefficient of the substance between ether and water is 2. We are provided with 1 liter of ether which may be used in one lot or two installments of 500 cc each. Using all ether in one installment, let x gram of substance be extracted in the extracting solvent. Then the amount of substance left in aqueous layer is a minus x gram. Therefore, concentration in water is A minus x upon 1000 and concentration in ether is x upon 1000. According to distribution law is C upon ether and concentration of water is equal to K. X upon 1000 upon A minus x upon 1000 is equals to 2. X की value 0.67 A. Thus only 67% of the total amount will be extracted. Extraction using 500 ml of ether. Let x1 gram of substance be extracted in the first installment of 500 ml ether. Concentration in ether is x1 upon 500 and concentration in water is equals to A minus x1 upon 1000. By this we get x की value 1 by 2a. 50% of substance will be extracted in one installment. The substance left in aqueous layer is a minus 1 by 2a is equals to 1 by 2a. Now 1 liter of aqueous solution containing 1 by 2 az of the substance is extracted with 500 ml of ether. By this we will get x to the value 1 by 4a. Hence 25% of the substance is extracted into ether layer. Total amount of substance extracted is equals to 50 plus 25 is 75%. Thus, when the substance is extracted using two 500 ml portions of the solvent, the percentage extraction increases from 66.66 to 75. Similarly, it can be shown that using the same 1 liter of the solvent in 4 installments of 250 ml each, 93.75% of the solution can be extracted. Thus, it can be concluded to do more efficient extraction. It is better to use a given quantity of solvent in small portions. However, it must be noted that it is not possible to extract whole of the dissolved substance. However, large number of extraction may be carried out every time the substance distributes itself between two solvents and some amount is always left unextracted. General formula for the substance left unextracted. A general expression to calculate the amount of substance left unextracted after a given number of operations is derived as follows. Suppose W gram of the substance is present in V ml of the solution made by using solvent A. It is extracted with extracting solvent B using V ml of B each time. K is the partition coefficient of the substance between solvent A and B. Let W1 gram be the amount of substance left unextracted in solvent A after first extraction. The distribution coefficient at the first stage is given as concentration of substance in organic solvent A upon concentration of substance in extracting solvent B is equal to K. W1 upon V upon W minus W1 into upon V is equal to K. W1 into V is equal to KVW minus KVW1, which gives W1 is equals to KV upon KV plus V into W. Now after the second extraction, if W2Z is the amount left unextracted in solvent A, then the amount of substance extracted is W1 minus W2 into Z. From distribution law, we get W2 is equal to W1 into KV upon KV plus V. Substituting values of W1 from equation 1, we get W2 is equal to W into KV square upon KV plus KV ka square. In general, the amount of substance that remains unextracted after nth extraction will be Wn is equal to W into Kv upon Kv plus V in की power n. To make extraction process most efficient, Wn should be smallest possible. This can happen if the term is made as small as possible. In this term, the denominator Kv plus V is bigger than numerator Kv. Hence, the factor Kv upon Kv plus small v is less than 1. Therefore, factor will be least for the greater value of n. Hence, the efficiency of extraction increases by increasing the number of extraction using only a small amount of extracting solvent each time. Thus, it is obvious that better efficiency can be achieved by keeping V small and n large. So, it follows that the multi-step extraction is more economical than the single-step extraction. Also, it is clear from equation 4 that Wn can never be equal to 0, however large values of n may be. That is, it is not possible to extract whole of the dissolved substance, however large number of extraction may be carried out. Every time the remaining substance distributes itself between the two solvents according to the distribution law. The principle of multi-step extraction is applicable to washing of precipitates. In the repeated washing of precipitates with small quantity of solvent, the impurities are extracted to a large extent. The principle of extraction is used in Parkes process for desilverization of lead. Silver is more soluble in zinc than in lead. The organic ferrous lead is melted and heated to 880 degrees Celsius, and then molten zinc is added. Molten zinc is immiscible with molten lead, hence form two immiscible liquids in contact with each other, and silver behaves as a solute which is more soluble in zinc than in lead. The partition coefficient of silver in favor of zinc is 300 at 880 degrees Celsius. Silver therefore passes radially from the heavier lead layer into the lighter zinc layer, which is then separated. By repeating the process 3 to 4 times, almost the entire amount of silver passes into the zinc layer. Hence, almost whole of the silver can be extracted from organic ferrous lead. In the determination of degree of hydrolysis, hydrolysis is determined as the process in which water reacts with salts to form an acid and a base. Some terms related to salt hydrolysis: hydrolysis constant. A general hydrolysis reaction of a salt Ba can be written as Pa plus H2O gives us Ha plus BOH. Applying law of chemical equilibrium, the equilibrium constant can be written as K is equals to Ha into BOH upon BaH2O. Since the concentration of water H2O is very large, it is regarded as partially constant, where Kh is the hydrolysis constant. In expression 2, Ha and BOH are the molar concentrations of acid and base produced, and Ha is the molar concentration of the unhydrolyzed salt. The above expression can be written as Kh is equals to free acid into free base upon unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt may be defined as the fraction of the total amount of salt which is hydrolyzed at the point of equilibrium. For example, in an aqueous solution of aniline hydrochloride, 80% of it hydrolyzed into aniline and hydrochloric acid, then the degree of hydrolysis is 0.80%. The degree of hydrolysis is represented HH. Mathematically, H is written as H is equals to number of moles of salt hydrolyzed upon total number of moles of salt. Expressions for degree of hydrolysis of different types of salts. The salts of strong acid and strong base such as NaCl, Na2SO4, KCl, KNO3 do not undergo hydrolysis. Therefore, for such salts, expression for KH and H are not written. These constants for the other three types of salts are discussed here. Salt of weak acid and strong base. The hydrolysis reaction of the salt Ba is written as Ba plus H2O is gives as BOH plus HA. In aqueous solution, Ba and strong base BOH undergo complete dissociation, whereas HA being weak acid remains undissociated. Therefore, we can write this. Thus, the salt of weak acid and strong base undergo anionic hydrolysis. If the initial concentration of the salt is C moles per liter and H is its degree of hydrolysis, then we have A minus plus H2O gives us OH negative plus HA. Initial concentration C and 0 0, concentration at equilibrium C1 minus H and CH. Hydrolysis constant is given by KH is equals to OH negative ions into HA upon A minus, which gives us CH square upon 1 minus H. If H is quite small as compared to 1, then 1 minus H is equals to 1. Above expression becomes KH is equals to CH square. H square is equals to KH upon C. H is equals to root of KH upon C. And H is directly proportional to 1 by root of C. Thus, the degree of dehydrolysis of a salt of a weak acid and strong base is inversely proportional to the square root of its molar concentration. Salt of strong acid and weak base. The general hydrolysis of reaction for salt Ba is written as the salt Ba and strong acid Ha are completely dissociated. Therefore, we can write the B plus H2O gives us BOH plus H plus. Hence, the salt undergoes cationic hydrolysis. In the case, hydrolysis constant is given as KH is equals to BOH into H plus upon B plus, which gives us CH square upon 1 minus H is equals to KH. As H is much smaller than 1, therefore above equation becomes CH square is equals to KH, H square is equals to KH upon C under the root, or H is equals to root of KH upon C. Salt of weak acid and weak base. Salt of weak acid and weak base Ba undergoes hydrolysis as Ba plus H2O is equal to BOH plus HA. The weak acid and weak base are weakly dissociated, but the salt Ba is completely dissociated. Thus we can write this. Thus it involves both cationic hydrolysis as well as anionic hydrolysis. At equilibrium, concentration of reactants is C and products are 0. At concentration at equilibrium becomes reactants की concentration 1 C1 minus H and products की concentration CH, which gives us H square upon 1 minus H का whole square. In case of this salt, H is much smaller than 1, thus 1 minus H is equals to 1. Therefore, above expression can be written as KH is equals to H square, H is equals to root of KH. It is important to note that this expression does not involve concentration term C. Hence, the degree of hydrolysis of such a salt is independent of the concentration of the salt solution. Application of distribution law in determining the degree of hydrolysis. Aniline hydrochloride is a salt of weak base and a strong acid. Its degree of hydrolysis is determined as followed. Step 1. Determination of hydrolysis constant. Aniline hydrochloride is hydrolyzed according to the reaction given below. The hydrolysis constant is given as C6H5NH2 plus H2O. To calculate the above concentration, an aqueous solution of aniline hydrochloride of known concentration is taken with a known volume of benzene. On straining, the mixture separates into two layers. Free aniline gets distributed between water and benzene, while HCl and unhydrolyzed salt remains in the aqueous layer as shown. Determination of concentration of free aniline in the aqueous layer. A known volume of benzene layer is taken out and the solvent is evaporated, then the weight of aniline left behind is found. From this, the concentration of aniline in benzene layer is calculated. The concentration of aniline in aqueous layer can be calculated using distribution law. Second, determination of concentration of free HCl in aqueous layer. From hydrolysis reaction, it is clear that number of moles of HCl set free is equals to total number of moles of aniline produced. Further, total amount of aniline produced, amount of aniline present in aqueous layer plus amount of aniline in benzene layer. The concentration of free aniline in aqueous and benzene layer is calculated in step 1 above. From these values, the number of moles of free HCl produced is also calculated. From the above volume of aqueous layer and the number of moles of HCl, the concentration of free HCl in aqueous layer can be calculated. Determination of concentration of unhydrolyzed salt in aqueous layer. Again, from hydrolysis equation, it is seen that the number of moles of aniline hydrochloride hydrolyzed, total number of moles of free aniline or HCl produced. The quantity of RHS has been calculated in step 3 above. Therefore, the number of moles of aniline hydrochloride hydrolyzed is obtained. When this is subtracted from the initial number of moles of the salt, the number of moles of unhydrolyzed salt can be calculated. From the volume of aqueous layer, the concentration of unhydrolyzed salt can be calculated. Substituting the values calculated in steps 1, 2 and 3 in equation 1, the hydrolysis constant Kh of the salt can be calculated. Calculation of degree of hydrolysis of aniline hydrochloride. After calculating the hydrolysis constant Kh as discussed above for a solution of the salt having concentration C moles per liter, the degree of hydrolysis can be calculated using this expression. H is equals to root of Kh upon C. Thank you.